Great. Okay, let's start. Can you hear me all right? Hello? Okay, everyone's awake. I know we're all hungry, we're all waiting for lunch, so I'm going to keep this as short as possible. Hello, welcome everyone to my talk, Machine Learning in the Browser. And I hope that the people in the back know that I'm starting because the clock is not running yet. Anyways, I'm just gonna start. So I want to talk to you about machine learning, and the title of my talk says DeepLearn.js because at the time I proposed the talk, it was still called DeepLearn.js. Nowadays, you probably heard of TensorFlow.js, which is the, I'm guessing it's either public beta or it's already version 1. And yeah, the nice thing is that it runs in the browser, so this gives us the possibility to actually utilize it as front-end developers. So let me start off by introducing myself. This is me. My name is Lian Li. And just for reference, so you know, this is not me. This is a desk. There's a company, a Taiwanese company that builds aluminum towers for PCs, and they incidentally have the same name. So while I was growing up in Germany, people would always discover this company and then tell it to me. For the 30 years that I'm on this planet, they would always introduce it to me like, you have never heard about this before. Like I have never Googled my own name or whatever. So for example, this one friend posted this to my Facebook wall. And I was like, oh, if I was a computer, I would, ha 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 ha, get it? And he thought this was so funny that he liked his own post and then posted another smiley face, just in case you didn't think this was funny because this is hilarious. So yeah, this has been haunting my whole life so far, and in my current company, it took all of 3 months for them to discover it, and they would be like, oh my God, is this someone else? I mean, the article is in Dutch, but it's clearly about company. So it's clearly not a person, and then someone discovered that there's also a website. I mean, like I said, I've been in this industry for almost 10 years. Of course, I have Googled my name before. I know of this company, so please don't tell me about it. But if you want to follow me, the person, you can do that with this handle. This is how I'm known on the internet, Chimney42. I'm trying to get into Mastodon, but it's like no one's there. So maybe you could like try to get it rolling, and then I might feel more inclined to post on Mastodon once a year or so. Cool. So I'm a software engineer for a company called Container Solutions. We are a consultancy that deals in programmable infrastructure. This has nothing to do with that. So this is just my day job. During the night, I call myself a machine learning enthusiast, which is just a fancy way of saying I have no formal education whatsoever. I just started getting into it a few years ago. I was doing the machine learning course on Coursera by Andrew Ng. It's a really good one if you want to check it out, although it's quite math heavy, and it did cost me many nights and nerves, and I cried a lot. But on the other end of it, you now feel like you've done something with your life, which is nice. So yeah, like I said, this is about machine learning. This is my hobby. I do not know anything about it that I haven't gotten from the internet somehow, so I'm not entirely, I can never be 100% sure how much of what I know is true. You know, it's the internet. So anyways, to understand this whole thing that I want to show you, we need to talk a little bit about how machine learning works in general, in very broad terms. I'm not going to go into the whole algorithms, the whole math side of it, just a little bit so we understand what we're talking about here. So machine learning, which are different from what I call here expert systems, they work in a different way when they try to approach a problem. So in expert systems, we get an input, or we get the inputs that we want to put into the expert system, and we have the rules. So for example, if you have a function that always adds 2, then you would have the rules, which is +2, and the inputs are just all the inputs that you get for your function, and then you get an output at the end of your system. This is how you use it, this is what it's for. In machine learning, however, you get the inputs as well, but you also get the outputs for it. So instead of having the rules put in, you have the output put in, and then you get the rules from it. That's the basic idea, that you're not, you already have the correct answers, and you're just trying to find like a rule set that will match the inputs and outputs. It will almost never exactly match what it's supposed to predict in the end, but it's like, it usually is a good approximation of it, what it is, and in the fields where we use machine learning, it's so fuzzy most of the time that there's no real true or false anyways. So what it comes down to is the data, the input and the output that are really important when we deal with machine learning problems or projects. All right, so the way that machine learning works or learns is very similar to how people or animals in general learn, which is through experience, which is the number of data points. So if you have broad, diverse experience, you have a big number of different data points. And then on the other hand, there's repetition, which is going through your data points, the number of times you go through your data points or data set. So that is the number of your training iterations. So ideally, you would have a broad experience, and then you repeat on it, you iterate on it a lot. That was just machine learning in general, but also, as I talked about before, we do machine learning in the browser today, and the nice thing about that is if it runs in the client, we have a few advantages that we wouldn't have otherwise. For example, there's a speed factor, a speed increase. We don't have to wait for the server to answer us with the correct prediction, for example. So it's going to be faster, hopefully. Then if you have your model on the client, it doesn't matter whether you're online or not. Now, if we do PWAs nowadays that are offline first, mobile first, it might make sense to always have the most current model on your client, be it the browser or your phone, so you're always able to do predictions. And then another advantage that you could find is security. So if you have sensitive data on which you want to make predictions, you might not want to send that out to the cloud or something, to some machine learning library of Google or Microsoft or whatever. So that would also make sense to then have the models that make the predictions on your client. Right, so let's talk about a problem, because I find it's easier to understand how machine learning works if we have a problem that is that we as humans can understand, because most of the time it's a lot about data and numbers, and it's kind of harder for humans to be intuitive about it. So the example that I chose is complementary colors. So complementary colors are like the opposite colors of a color. So for purple, it's going to be yellow, and for orange, it's going to be blue, I believe. So it's the color that is, you know what it is? Because it's hard to explain. If you don't know what it is, ask your neighbor. Maybe they can explain it to you. So the machine learning algorithm I'm showing you is supposed to predict the complementary color for any given color so the color is represented by an array with 3 elements, which is the RGB value of the color. Sorry. When we're talking about these machine learning terms, we need to kind of be on the same page about what they mean. So I'm going to go through a few terms. So we know what we're talking about later on. So in conventional programming, you have, as I said before, the input, and you feed the input into a function. And then out of that, you get an output. So the input is set, usually. It's immutable. It's just what you get from outside. You put that input into a function, and then you get a specific output. So the function and the output are tied together. If you have a different function, you get a different output. If you have the same function, you feed the same input, and you should get the same output. Now, in machine learning, the inputs are called features. Each feature, you can have a lot of different features, and each feature is something that needs to usually have a value in each data set. So for example, if we were to predict complementary colors, and we have 3 elements, which is red, green, and blue, then we would have 3 features for this problem. The function in machine learning would be the network. So in this specific deep learning network, neural network example, the function is the network. Now each network consists of multiple nodes, and each node is also its own function. So network is usually a function of functions. And then from what we get out of the network, that's what we call the prediction. So the same rules apply, that the features are usually set, the network and the prediction are tied together. So you would get the same prediction for the same network in which you feed the same features. Now, additionally to what we have in conventional programming, we have in machine learning the outputs that are given. So not the output here, which is the prediction, but the actual output that we use to train our model. So the output in our training set. And that is called, I would call it here, the desired output. This is what we want the network to predict at some point after we train it. And in machine learning terms, this desired output is called the target. Kind of makes sense. This is the target to which we want to train our network. So we have features, which are the inputs. We have a network. We put the features into the network. We get a prediction. And then we try to do something so that the prediction and the target are really similar to each other. Right, and then for this to work, for the model to be better, to be trained, we need the features and the target values, which is our data. And one of the reasons why I picked complementary colors as an example is because there is a mathematical solution to how to get the complementary color of any given color. So we don't have to take a lot of time and put it into data mining and getting the data, because we can just create a data set however big we want it to be on the fly. So in code, this is what it would look like. So first we import TensorFlow as a STF. Then we have this function that's called generate data. It can take any size, and then we create 2 arrays. So features and targets are 2 separate arrays, and it is imperative that the order, even if you shuffle them, but the indexes have to correspond to each other. So if you the 5th entry in features needs to correspond to the 5th entry in targets. So and then we have this loop, and during this loop, we create a random color array, and we compute the complementary color for it. So it's just an array with values, with 3 elements, values between 0 and 255. And then we take this color and we normalize it. And by normalizing it, we basically assign a minimum and maximum value, which makes it easier for the algorithm to understand that there's a cap at 255. And we push those into our arrays. Then we need to define the shape of this matrix. The shape in this case is the size of the array and the number of elements in the input and output vector. And then we have to create these 2D tensors. So I don't know if you've been to Dominic's talk yesterday, because he talked a little bit about tensors and TensorFlow.js. So this is a 2D matrix, or a two-dimensional array. All right, so I've created this checklist for us to go through for when we want to train or build a self-learning algorithm. So what we need is some data, which we now created. We can create data at any size that we want. Then the next thing is that we need a network. We need to do something with the network, and then it's gonna be awesome, clearly. So let's talk about this network thing, because this is where TensorFlow.js comes in. So TensorFlow.js is a port of the TensorFlow library in Python. Has anyone ever worked with TensorFlow in Python? I'm seeing a few hands going up. That's cool. So maybe you've not worked with TensorFlow, but maybe you've worked with Keras, which is more a higher level API for it, or wrapper. It's kind of similar to how TensorFlow.js is to DeepLearn.js. DeepLearn.js was a very bare, hard-to-use library, and TensorFlow.js is, in its abstraction level, closer to Keras. And the nice thing about TensorFlow.js is that it uses WebGL, so you can then use the graphics card to do all these massively parallel calculations, which makes your training your model faster. All right, so we need a neural network. You might have a general idea what a neural network is, how it looks like, how it works, so I'm just gonna try to go over it as abstract as possible. So each neural network consists of these columns, which are also called layers or also called tensors. So a column can consist of any number of nodes. So each of those dots is a node. And you can have, like I said, you can have multiple layers or tensors. Usually you have a bunch of them in the middle, which are called the hidden layers. And then you have a layer at the beginning, usually the left, and one at the right, that's the output. So left is the input layer and right is the output layer. So in this example, we would have 3 features or 3 inputs and 2 outputs. So in our example, we would have to have 3 output nodes because we want the 3 values for our GNB. And then in this neural network, which is a densely layered network, each node is connected to all of the nodes in the layer that succeeded? Yeah, that come after. So all the nodes are connected to all the nodes in the layer after, not to the layer, not to the nodes in the same layer. It's always the one after. Right, so let's look at a single node in this neural network. So we have our inputs. In this case, we have 3 nodes in the layer before. Inputs are x1, x2, x3. They are different inputs. Then we do something, when we calculate something. In this case, I'm taking the sum of it and then output that value to the next layer. So now I'm outputting the same value to all the 3 nodes in the layer that come after. Now you're thinking, if that's all I'm doing in this node, then all the other nodes in this layer will also output the same value because all I'm doing is adding all the inputs that come before, and that's the same for all the nodes in this layer. So what's special about these nodes is that they have weights, and weights correspond to each of those inputs, and then the weights that basically make that the output is different from this node to other nodes in the same layer. So it's a bit complicated, but I promise it will get more clear. So the weights are the property of a node, and we have a weight for each input. So x1 gets its own weight, x2 gets its second weight, and so on. And the idea of the weights is to then basically define how important this input is to predict the thing that we want to predict. So let's say if we have, let's say housing price predictions. That's a good example that's usually used a lot. We have a number of rooms, square footage, number of bathrooms. And then maybe you have a feature that is color of house, whatever. And then it turns out that this is not very important to predict the price of the house, so then this input will probably get a really, really small weight. So then because the weight is multiplied with that input, And if it's really, really not important, then you would multiply it with a really small number. Yeah, and then the other thing with the weights is that all the weights that are in this model, they basically make this model the way that it is. So these weights determine what the output will be, what the prediction will be. So the whole model basically comes down to these weights. Okay, let's talk about the layers that are in this that are used in this model. So we have dense layers. They are just the ones that I just explained to you. That each node is connected to all the nodes in the following layer. And what's happening in each of those nodes is that we multiply each input with the weight, like I explained before, x1 and weight 1, x2 and weight 2. And then we feed that result into an activation function. Usually, you don't have to have an activation function. Some make more sense than others. In this example, I'm just using one at the end, and I'm going to explain to you what it does. And then afterwards, after we feed our result into this activation function, we then add a bias. A bias is used if there is to represent a natural inclination towards something. So again, in housing price predictions, if you would just multiply the number of rooms with some weight, you might get something where if you just have one room, you'll end up at like $10. But you know that housing prices always start at, let's say, $10,000. So you would add a bias of 10,000 to the result. This is a very simplified example, but this is basically how bias works. I need to speed up a little bit. Okay, so this is what the code looks like. And again, I hope this makes it a little bit more clear how we can use this. So on the left side, I have the control code. On the right side, there are a few helper methods that I wrote. First thing we need to do is create a model. And that is something we get from calling the sequential function on TensorFlow. The sequential function basically just says this model has layers sequentially. There are some weird architectures that you could use for models, but let's go with the easy one here. And then we want to add a dense layer to this model. So the dense layer is added by calling add, and then we pass in a config to this dense constructor. And the config is just what we see on the left, this JSON object that is units and input dimensions. So we have 3 nodes in this layer, and the input dimensions, so the input that we get in has also 3 elements. And this is our input tensor. So we need one on the left side that has one node for each input. Then we add more dense layers. In this case, I arbitrarily chose to add 3 hidden layers. That is just from an example I took, and it worked fine, but there's no guarantee that this will work for any of the things you want to use it for. So in this case, the configuration we add has the unit number of units, and then we specify that we want to use a bias here. And then we have to add the output layer, which is another dense layer that now uses an activation function. So again, it's using 3 units because we have 3 elements in our output. The activation function is named ReLU here. It's short for rectifier linear unit, and what it does is it returns the value. If you pass in x into the activation function, you get x back for all the values where x is bigger than 0, and for all the values where x is smaller than 0, you get 0. So this basically just makes sure that you don't get any negative numbers or values at the end of this. All right, so we have our data, we have our network. Now what we need to do is to do something with it that's awesome, and then we get some profit out of it. So the awesome thing that we're going to do is the training. And the training is the heart of machine learning. It might sound a little bit daunting or complicated, but I swear it's not that hard, actually. So what we do during the training is actually 3 principles. We find a metric, we change something, And then we check that metric again. And now hopefully if our metric performs better, we just do the same thing over and over again until it's not better. Or if it's not better, then we just change it back or change something else. It's a pretty simple process, actually. So the metric that we are using in machine learning is called the cost or loss function. So we have a, this graph represents on the x-axis, that's x, the input. So in this example, we only have one dimension, one input feature, and y, that is our output. That is the thing, the value that we want to predict. So this purple line is the target. This is just the reality that we want to predict. This is the thing that we want to approach. The line, the white line, the prediction line, is what our model actually currently predicts. And what we want to do is take these points that are on the same axis, so they have the same value for x, and we want to make this difference as small as possible, because if the difference is small, then we're predicting really well. I'm sorry, I have to really speed up. So all of these values, all of these differences make up our cost or our loss. That is the metric that we want to reduce. The way that we reduce it, the thing that we change is what the optimizer does. So in this graphic, the x-axis is the weight. So if we have the weight of 20, so if a weight is 20, then our loss is really high. So that means that the difference between the target and the prediction is very high. And if the weight is around 100, it's really low, so that's where we want to go. And the way the optimizer works is that we start at this one point, we take the derivative, which is the slope at that point, and then we take a step to the left and a step to the right and get the derivatives there. And then we just go to the direction where the derivative is less, where the slope is not as steep. Because where the slope is not as steep, that is where we approach the minimum, the lowest point. And this is how it works. So we basically just check the slope, and we walk into the direction where the slope is less steep. And then we just take a step there, we calculate the derivatives over there, and then we take a step in the other direction, and so on until we hopefully get to the minimum at some point. This is the principle of machine learning. I'm sorry that I had to go through it so fast, but it's not supposed to be really, really complicated. It's just expressed in complicated formulas. So, but in TensorFlow.js, it's actually super easy to use because, as you can see, it's not that much code. What we actually do is define a learning rate. The learning rate is the size of the steps that you walk from, that I just showed you. And then we have to define which training optimizer we want to use. In this case, we use the SGD optimizer, which is called the stochastic gradient descent, which is just what I showed you. Gradient descent is just walking down that hill, basically. And then we compile the model. We have to define a function for the loss. So this is how we express our loss. In this case, it's called the mean squared error. And what it does is it's taking all the differences that we calculated, squaring them, so big errors get really exaggerated and small errors are not that important, basically. And then we take the mean of all of those squared errors. Okay, so we have the data, we have the network, we set up the training, now we can run our algorithm. So everything we've done up till now was just specifying and defining what we're going to do. Now it's runtime. So, I have 1 minute left. So, this is basically a kind of visualization of what happens when we run the training. Of course, it's just a very basic overview, so this is not, don't tell your children this is how it works. So we we start with data, we put in the input at the network beginning, and then we calculate all these values, propagate the data through our network, this is called forward propagation, until we get this prediction. In this case, the prediction is 3. Then we look into our data again and check our target, our desired output, which in this case is 2, so we're off by 1. In this case, I'm just taking the difference, not any fancy stuff. The difference is 1, We take this difference, feed it to our optimizer, and our optimizer knows everything about our network, puts this one back into it, and that's called backpropagation, backwards propagates the data through the network, and during this time changes all the weights, so it is then able to reduce the error, reduce the loss in each of those nodes. And in real time, it's not doing that for each single test data point sequentially, but at the same time. That's why we need graphics cards, so we can do this parallelly. So we're calculating the losses for all of our data points at once, and then taking the loss of all of them as one value, and then passing that into the optimizer once. So we're taking a whole batch, actually, and then calculating the loss on a whole batch, and then pass it back through. So, don't know how much time I have. You still have a bit of time, right? Sure, okay. So the way that we train it during runtime is we have to define a batch size. Like I said, this is the number of training data that we do, that we run through for one iteration. And the number of epochs is how often we go through the entire data set. What we have to do is call the function fit. So we fit the model to the features and targets that we created at the very beginning when we created our data, feed the configuration to it, and then this is an async function. We get a history back. In this case, I'm calculating the average loss of the training iterations that we made. Okay, let's see. I'm really, really stressing about it because this is highly risky what I'm doing here. So, okay, this is live demo now. So as you can see, we have some values that we can play with. Now I started this. So the input color is always the same. The target color, of course, always is also always the same. And on the right side, you can see the predictions. And you can see how the color changes a little bit. This is actually already quite good. So I'm going to try and make something that looks a little bit, that will maybe take more time or just be a little bit harder. So, okay, so now you can see that it was predicting. So first of all, this is much quicker because we have less training examples to work with. And then also, as you can see, like it was at the same color for a long time, and then it just tried something else, and that seemed to work a little bit. It like got out of its rut, kind of. And then it like slowly approaches the real color. We would have to maybe increase the number of iterations so we can see it be better. Yes. Yeah, so it gets really to a point where it's hard for us as humans to distinguish that there is still an error. So this is kind of like going back and forth now. It's not really getting better, which is probably because we can't really get the exact minimum all the time. We just have to kind of walk around it. All right, that worked surprisingly well. That was great. Okay, so I'm gonna just show you a few links that you can take pictures of. Of course, I'm going to put the slides on my Twitter account, and it's also on Sketch, I believe. So the first one is the project. You can check it out and then play around with it yourself. You saw that you could change the values on the top of the website. This is jstенsorflow.org is where you can get TensorFlow and learn more about it and see more examples. The next site is an introduction to deep learning. It's actually really good to read. And the last one is the machine learning course, which I encourage you to do if you have the time and lost the will to live. Also, the company I work for, which is an amazing company, is hiring. If you ever look to move into one of those cities, or we've opened a branch in Montreal, you can come up and talk to me. Also, you can, of course, always come up and talk to me. And thank you for your time.